Our first speaker is Brett Falk from Penn. So Brett, take it away.
All right, thanks. And this is joint work with Alon Benheim and Jerry Tsoukalis. And so I want to talk about quadratic voting. So in terms of a voting model, here's an example of a proposal from Uniswap. And the point of this is just to think Uniswap uses like Compound's voting model where somebody makes a proposal and it's a yes/no proposal. And it can be something like, should we deploy Uniswap v3 on the Filecoin virtual machine? So this is the kind of model of voting we're thinking about of these yes/no proposals. And so, most on-chain voting is stake weighted, and your voting power is proportional to your stake. And quadratic voting is basically this question of saying, what if your voting power were proportional to the square root of your stake instead of your stake, right? So that's the main question. What changes when your voting power is now proportional to the square root of your stake? So one place that does this is Axelar. Axelar is a cross-chain message passing platform. And here they show if you have 52 million tokens staked, your voting power is like the square root of this. And now, actually, there's a kind of caveat here, which is they do this. The staking is for block production and for cross-chain message passing, and the quadratic part is only for the cross-chain message passing, not for the validation. But they do implement this here. And on all the governance platforms, people have proposed quadratic voting at some point. So in Polkadot, there's discussion, should we go to quadratic voting? And Uniswap, there are discussions sometimes about should we move to quadratic voting? They have not actually happened, but there's discussions about it. The other place maybe you've heard most about quadratic voting in the blockchain space is this Gitcoin grants program. This is a little bit different. This is quadratic crowdfunding, and so the model's a little different. But the idea in Gitcoin grants is you have some user I, and they contribute some money via I of P towards some project P, and the project doesn't receive the sum of these donations. It receives the sum of the square roots squared. Now, if you think about this for a minute, right, there's a problem, which is that this may run a deficit, that the amount of money coming in from all the people may not equal the money going out. And so this deficit has to be made up by people. And in Gitcoin, it's made up by philanthropic donors like the Ethereum Foundation. But this is also a sort of quadratic mechanism that is probably the most established in the blockchain space. But in this talk, we're going to be thinking about the kind of quadratic mechanism for voting for these binary proposals. Oh, actually, what I want to say too about all of the quadratic mechanisms we were talking about, they have this problem that if your voting power is proportional to the square root, you need, it incentivizes you to split your tokens, right? You get more voting power to make 10 weight 1 votes rather than 10 weight 10 vote because you only get the square root. So you need some kind of Sybil resistance mechanism. Gitcoin has this whole sort of identity verification framework, and they have Gitcoin Passport. It's kind of neat. We're not going to talk about that specifically. We're going to sort of assume that there is some Sybil resistance mechanism, but that's sort of a big issue you need to resolve if you're ever going to think about quadratic voting in practice. So here is sort of the model we've been thinking about, which is sort of aligned with the original quadratic voting models. You have a bunch of voters. They are going to vote on a binary proposal. It's like a +1, -1 proposal, and they have some utility, and everybody gets some different utility if the proposal is passed, and they have to choose some vote weights. So voter I votes some amount VI, and the outcome is just the sign of the sum of these. So if the votes are positive, then it's +1, and if the votes are negative, it's -1. And in our model, the utility you get is you get UI if your choice was taken, otherwise you get 0. And you could easily, in other papers people have done, you get a negative, and it doesn't really matter. We just happen to say it's 0 here. Right, so it's a binary proposal, and you get sort of discontinuous payoffs depending on if your outcome is chosen. And we'll be focused on the net utility here, and the net utility is just the sum of the utilities that everybody gets. And the baseline that this often gets compared to outside the blockchain space is the sort of one person, one vote setting, where basically the only thing you can do is you vote your type, right? You vote +1 if you want +1, and you vote -1 if you want -1. And in the quadratic voting space and in the blockchain space, we're going to be focused on this question where there's some cost to voting. There's some cost function buying V votes, cost F of V. And we can look at a range of things. We're going to look at cost functions that are basically polynomials where the cost is V to the M. And so if you have M equals 1, then the cost is linear voting, is a stake-weighted voting that you would normally have, that there's some linear cost to staking. And M equals 2 is quadratic voting. But you can also imagine different weights. And so the individual utility that somebody gets, voter I gets this UI, which is specific to voter I, and there's some aggregation function psi, which was like maybe the sign of the sum that takes in all the votes and decides whether the outcome is plus or minus 1. And then you have to pay this cost F of V to vote. So this is the voter I's utility. And then the net utility is this sum. And now the problem with this is that basically, if you do something like, if you're trying to maximize net utility, the quadratic, if the cost function goes up, you've just made everybody worse, right? So you need to kind of fix that. And so the way this is fixed in the quadratic voting literature is you need some way to redistribute the voting costs. If you charge people more to vote, right, that's going to bring down their utility. So you need to like give those charges kind of back to people. And so there's some redistribution mechanism, and you want the redistribution mechanism to be budget balanced, meaning that the amount you take in is the amount you redistribute back. And the nice thing is if you make it so the redistribution depends on everybody's vote but yours, then each voter, when they're making their voting decision, they can basically ignore the redistribution because it doesn't affect their payoff. Right? They're going to get the same redistribution no matter what they vote. So this is the standard trick that's used in all the quadratic voting paper. So the payoff function from a user now is they get UI times the event that their outcome is chosen minus the voting cost plus this redistribution. And so their goal is to choose the VI that maximizes this. Right? This is going to be the voter's maximization problem. And because this last term, right, doesn't depend on their vote choice VI, we get to just ignore it. And this, again, works in all of the in the quadratic voting papers. It's really nice. So a voter is trying to choose the votes that maximizes this kind of thing. So now the tweak that we're doing on this model is that in prior works on quadratic voting, they assume that people have sort of heterogeneous preferences and they know their preferences perfectly. And we're considering this model where people have imperfect information. And so the motivation for this is a vote like this. So here's an example vote from Compound and saying, should we change these collateral factors? So should we change the collateral factor on BAT from 65% to 62%? And if you think about that, like, I kind of imagine that it's not that some people get huge utility from a 65% collateral factor and other people get great utility from a 62%. It's really like everybody kind of wants to choose the collateral factor that will be the best for Compound, right? That will get them the highest returns on their comp tokens. And it's just nobody really knows which is the better one of these two choices, right? You may have some guess and maybe you've done some modeling that you think this collateral factor needs to be higher or lower. But nobody really knows. And so this is what we're going to model. We're going to model this idea where you have a bunch of voters and they all have partial information. And we want to think of the voting mechanism as like a crowdsourcing or information aggregation mechanism as instead of a way to like determine the majority opinion. I generally like this model a lot, and we've considered this in a couple other cases before. One of the first places we considered this was in what you'd call like direct voting. So imagine you wanted to vote for this collateral factor. Instead of doing it the way Compound does it, where it's a yes-no vote, somebody proposes the collateral factor should be 62%. Instead, you say, why doesn't everybody propose a collateral factor? And the system will take the weighted average of everybody's votes, right? This seems like a very natural way to choose an interest rate or a collateral factor or some real number parameter for the system. So then if the user votes for parameter QI with weight VI, then you just get this weighted average. And so then the question is, what happens in this when people have partial information, and does this incentivize them to gather information? So this is an early paper with Jerry Tsoukalos about how to think about this. We also looked at this partial information in the case of approval voting. And so approval voting is really interesting. It's like when you need to choose a subset of things, or if you need to choose from a subset. For example, if you're electing block producers to a committee, you can now, in approval voting, approve of multiple candidates. You can say, I'd be okay with, a 62% rate or a 63% or a 64%, but not 65, 66, 67. And every approval gets your full weight, so if you're not splitting your weight between these. And so in this case, we can also look at how does approval voting do as an information aggregation mechanism as compared to a place where you only have a single vote, right? So this is another kind of question that we looked at. And so now we're going to look at, in this work, we're going to look at how quadratic voting does in this model. So here's kind of the model. We have a compound proposal. We have a Uniswap proposal. It's a binary proposal. There's sort of a good option and a bad option. So either 65% is a good collateral factor or 62%. One of them is better than the others. And voter I has some probability PI of identifying the good proposal. Right, so there's some imperfect information, and the PIs are known, so you know if you have some information about this or not. You know if you're an informed voter or not. And voters get this UI payoff if the good option is chosen and zero otherwise. And if we just without loss of generality, we can just say the good option is 1. And so the voter is going to vote, a positive or negative based on their signal. And so their signal is, their PI is the probability that their signal kind of points them to the good option. And so then the probability the good option is chosen is the probability that the sum of these vote weights is positive in this case. And the VI is going to be the decision variable that the voters get to make. So the voter has to choose their VI to maximize this, this utility, right? This is their utility. This is the probability the good option is chosen, the cost, and then this redistribution. And again, we're going to be trying to say, what is the mechanism that maximizes the net utility for everybody, right? So the goal is to build a platform that makes kind of the best decisions. So this is going to be the one that maximizes utility. And so the nice thing is when we add this up, because this is budget balanced, these terms just cancel. And so we're just trying to maximize this. And so it actually is the same as we're just trying to find the maximizing the net utility is the same thing as maximizing the probability that you make the right decision, right? So, so the main question we ask is, what cost function is going to maximize the probability you make the right decision, given that each voter is maximizing this their individual cost? Okay, so that's the model we're in here. And just as a basic background, right, in the one person, one vote setting, where you don't get to choose how many, there's no decision for the voters to make, they just all are going to vote their signal, then the probability of getting the right decision is basically the probability that this thing is bigger than a half if they're n voters. And this is a Poisson binomial, and so you can get a closed form for this. And so this is kind of like a reference point, and this ends up coming out in our calculations. Okay, so now the one sort of technical thing here is that when we consider these different voting mechanisms with a different parameter m, so whether the m equals 1 is linear voting and m equals 2 is quadratic voting, turns out that there are actually multiple equilibria under these different systems. And so when we want to compare these mechanisms, we need some way of doing that. And so we took a sort of a very conservative way of considering a partial ordering on these mechanisms, because the question was asking, like, is linear voting or quadratic voting going to be better as a crowdsourcing mechanism? And we find that there are multiple equilibria and we need to compare them. So we said, basically, this M1 will be worse or less than M2 if it's missing some better equilibria. So the maximum that you get in this green, the maximum equilibrium here, is worse than the minimum you get by adding this. Then we say the M2 is better, right? That seems like something we can all agree on. Like if we just add this, it's strictly better. You can't make anything worse. And similarly, M1 is worse if it's only got worse equilibria. If the maximum in this set over here, right, is less than the minimum over here, then again, we'd say this M2 is a better mechanism. Right? So that's when we talk about like the ordering of these mechanisms, that's what we're going to talk about, because they end up having multiple equilibria. So we started with looking just at the two-voter case, and this ends up being already like a little bit of a complicated combinatorial problem because voters are trying to maximize this discontinuous kind of thing, but we can categorize things completely. And so here's the possible space, and so for all parameters, we can get all of the equilibria. And so the way this is written is the equilibria on top are what you get from linear voting, and this is the equilibrium you'd get from quadratic voting. And so the green region is where linear voting is better than quadratic voting under this notion of ordering of mechanisms. And the red is where quadratic voting is better than linear. So depending on your parameters, which is basically the parameters are how accurate the people are. It's the utilities, right? The parameters in the system are people's utilities and how accurate the two voters are. It depends. You get better crowdsourcing from linear or quadratic. So it's actually, there isn't like a clean answer of saying that quadratic voting is going to be strictly better, right? Sometimes linear voting is better. And there's a bunch of space where they all lead to the same equilibria, and they're then identical. Then we can do the same thing in the three-voter case. It gets a little bit more complicated, but we can calculate all of the possible equilibria. So like one equilibrium is 1-1-1 would be all the voters just vote weight 1 for everything, right? This 3-1-1 is the case where voter 1 acts as like essentially the dictator. And so voter 1 votes 3 and that overwhelms everybody else and you ignore them, right? And you can imagine that if voter 1's information is so much better than everybody else's, maybe you'd want to have a system where that would happen, right? And that's an equilibrium. We can calculate exactly the region of space where that is an equilibrium based on now all these parameters. Unfortunately, now I can't easily graph it because now there's, P1, P2, P3, and it doesn't show up well on a two-dimensional slide. But we can calculate all the equilibria and the regions where they happen. And it just depends, like based on these things of what is the probability of different events. So this is like, this probability is voter 1 was incorrect and voter 2 and voter 3 were correct. If we say, what's the probability that this happened? This is the C1. And we see, this appears in these regions. And this M is, 1 for linear voting and 2 for quadratic voting and 3 for cubic voting if people wanted to do that. But this generalizes to any M. And so, we can solve things completely for these small voter cases. Now, as n goes to infinity, as you may, if we assume that all the voters have, independent signals, then you get a central limit theorem kind of result, right? You just get a concentration of measure that says basically like anything's going to work. It doesn't really matter if everybody is like a little bit informed and independent. Sort of anything you want works. But just to compare this to the original Lally-Weil stuff where there's, taught that proposed quadratic voting, in those models, there's no uncertainty. Everybody knows exactly what's going on. Voter utilities are UI, they can be positive or negative. And to get some cleaner results, they take the sort of discrete, they start with this discrete model and they say this is hard to work with, so they make it smooth, right? So you imagine instead of this discontinuous step function, they say let's smooth it out, just under the assumption that it will eventually get to be the plus minus 1 function at some point. And so their goal then was to minimize the expected inefficiency, where they defined inefficiency to be this. And at first it looks a little funny, but if you think about it, this is right the sum. If their utilities are plus or minus 1, this is sort of the best you can hope for is this sum of the absolute value of the sum. And this thing on top here's this, and this thing is going to be a plus or minus 1, and you basically want this to be +1 when this sum is positive and -1 when the sum is negative, and then these would cancel out. So this basically, you'll have a 0 inefficiency exactly when people vote like proportional to their utility. So that's the that's sort of the intuition for what they want. And then what they can show is that basically, if each individual is trying to maximize this, if you take the derivatives here, you get the derivative of the cost function here. And if you kind of make this assumption that if you squint at things, that this should maybe become constant, that it's not going to depend that much on any individual I. In that case, then a first order condition for a user's maximization should be f prime of v is some constant times this. And the quadratic cost function is exactly this thing, right, where the derivative is also linear. And so we'd get that this exact thing that's going to give us the 0 expected inefficiency. So that was their model that basically, if you have the intuition was, if you make this assumption that this is almost constant, then you get 0 inefficiency. And then they basically show that that as n goes to infinity, this actually is the case, that you have the expected inefficiency go to 0. So just to contrast this to the previous work, right? The previous work here is all about in the perfect information setting. So anyway, just to wrap things up, like I'm very interested in this, how do you design models for crowdsourcing this imperfect information? So we looked at direct voting a while ago, we looked at approval voting. In this case, we kind of looked at quadratic voting for binary proposals. Now, quadratic voting is interesting because it's not really a voting mechanism. You can have quadratic direct voting, you can have quadratic approval voting. It's like actually just a way for weighting stake. You can combine, you could have quadratic ranked choice voting, right? Just it's kind of orthogonal to the question of like how you actually aggregate votes. It's how you assign weight to votes. But I think there's a lot of interesting work here in terms of thinking about these kind of DAO mechanisms about if your goal is kind of crowdsourcing information for parameter settings or whether to deploy to Filecoin virtual machine or something. These are questions where you want some crowdsourcing of information. So, thanks.
All right. Thank you very much, Brett. Questions?
I have a really basic one, actually.
Yep.
So there's a slide where you show, I think, a player utility, and there's a probability in there. And I actually don't know what the probability is over. It's actually
Over which one?
Back.
Of this?
No, it's even quite a bit back.
Oh, early on?
It's somewhat early on.
Okay, yes, I'm sorry. Okay, sure. So here.
This is the
Yep.
net, right?
Okay, yeah. So the way we model things, we put this S term in. So basically you can think of SI will be a random variable about whether you choose the right decision. And so this is what I was saying, you could choose without loss of generality, you could say the right decision is 1. But so imagine the right decision is either plus or minus 1, nobody knows. And you get some signal SI, which is plus or minus 1, which is I think the correct answer is 1, if SI is 1, and I think the correct answer is minus 1 if and that's the probability here. So I know I have some probability that that I can discern the good from the bad. So I know that with 75% probability, I'm right. And so now this is the probability. So everybody knows when I cast a vote, I know I'm going to be right with 75% probability. I know you're going to be right with 80% probability. And now we all have to choose how much weight to put on our vote. So that's the whole game here. Right? We all know.
The strategy space is actually over the valuations.
Yeah, the strategy space is over the valuations, and the randomness is over the SI.
Okay, perfect. Thank you. Sorry, just
very dumb. No, sorry.
No, it's really good because it could have been like you observe. Signal, and then afterwards choose both whether to signal and.
So you can think of it as you observe the signal, but the only thing you can really do with the signal is since the signal is plus or minus 1, you just basically have to vote in the direction of the signal. Okay. And so. That's not really a constraint. It just comes out of the thing. But so you can just imagine that's the only thing you can do.
Awesome. Thanks.
Yeah.
Any other questions?
So I also have a basic question. So suppose that I have a big stake
Yeah.
but I want to increase my voting.
Yeah.
And we are under the quadratic voting.
Yeah.
Can't I produce multiple identities?
Yeah. So yeah, this is what I was saying. Yeah, this is the fundamental flaw with sort of all these quadratic voting kind of things. And so places that implement it, like Gitcoin grants, they have to have an identity verification thing. So in order to participate there, you have to go through some identity verification process, which makes it a little bit harder to sort of make these kind of Sybil attacks. But yeah, if you were going to implement this, you need some sort of identity mechanism.
KYC.
Yeah, I mean their thing is somewhat decentralized. You can gather these stamps, and you can link your thing to a GitHub account or to a Twitter account or to a LinkedIn account or something, and they view this as some sort of weak form of KYC. But yeah, you need to tie it to some form of identity verification if you want to do this. Yeah.
So just thinking a little bit outside of the model, like taking as example this voting on the collateral factor, you could imagine that, I imagine there are many people who are just voting to support the health of the platform, and they have imperfect information about volatilities. But I could be somebody who regularly borrows against that collateral asset, and I have a clear, I don't care what I think is the best for the platform. I know exactly how I'm going to vote. Can you account for a small fraction of investors?
So in this, we didn't consider that. In some of the other works, we did consider like what happens. This is a totally natural question. You want to say like, what if 5% of the voting stake or 10% of the voting stake, right? The whole thing, you're never going to win, right, if 90% of the voting stake wants something bad, right? But if you want to say there's some small fraction of the voting stake that has sort of counter incentives, right? How do different models account for that? We didn't look at it all in this quadratic voting setting. The equilibria that we ended up getting were like super complicated because it was all combinatoric, so we didn't make this smooth assumption. But in other models, we have some stuff, and it's actually really interesting. This is like actually, I think, a really cool question. It's another thing you might want to sort of optimize over, which is like your robustness against a set of bad actors, right? So a lot of the primary question I was asking is what's like the best information aggregation mechanism, but the secondary question or an alternative primary thing is of all these mechanisms, if you want to do like, we've been looking at this a little bit, but just in general, like a big picture question is, say you have direct voting, or you have this like binary yes/no voting, or you have approval voting. Which one of these is, say, most robust against, some small threshold of bad actors? And then you can say, given that there's, 5% of the people who are trying to minimize the expected utility, how does this work out? Anyway, so that's a question we've been looking at. I don't have anything to say on the quadratic voting setting, but it's a super interesting question.
I had a question about your like signal model. So it seems like you're assuming kind of independence between the different voters, and I think in the compound example, you might imagine the people are forming their signals from some joint thing that they're seeing. And so their signals are actually correlated. And how does the equilibrium shift under that?
Yeah, I mean, so we don't have the mathematics around the correlation. I mean, one problem with that, like obviously I don't want to have to assume that things are uncorrelated. It's super hard. I mean, once you assume a correlation, you have to actually give the form of the correlation. So that was sort of one maybe justification for this smaller looking at small voter size. If you look at like how many people are voting on compound, there's like 3 or 4 people who like determine the thing anyway. Maybe they are at least semi uncorrelated. But no. Look, that's an assumption we would love to get rid of. But to do anything mathematically with it, one is obviously uncorrelated is much easier to work with, but 2 is once you have some correlation, you have to give a specific form of the correlation, and then it opens all kinds of questions of how correlated, what's the correlation, and anyway. So unfortunately I don't have any concrete things to say about that.
Thanks.
You mentioned about the probability. Is that something similar to the conviction voting in Polkadot, where you tie in for a longer period?
So for us, the probability was really like the probability that you were correct, not the probability that you want to signal that you're correct, right?
Okay. Got it. Thanks.
Yeah.
All right. I think we'll have to wrap it up for this presentation. One more round of applause for that. Thank you.